Hello students, good evening. Welcome to another video of Vedantu Karnataka. This is Catherine, your physics master teacher. So you might have all seen the thumbnail that today we're going to do 5 markers. Before that, quickly can you let me know if I'm audible and visible? Let me also check. Yes. Okay, live. Hi Pallavi, hi Praveen, hi Sunita, hi Sana. I'm good Pallavi, how are you? Hi Teju. Hello everybody. Good evening, unknown. Ma'am, when release Sport Bank KCT? Hi, Chaitra. Thank you, Praveen. Hi, Joshi. Okay, so yeah, as you all saw on the thumbnail, we're going to do 5 markers. Okay, are you all ready? Shall we start? Shall we not waste a lot of time because we already lost some time? Are you ready? If you're all ready, can you put some fire emojis in the chat quickly? Then we'll start. Yes. Quickly, can you put some fire emojis in the chat? I'm waiting. So did you all start your preparations for exam 3? Okay. Teju's ready. Chaitra is ready. Pallavi is ready. So let's start. Question number 1. First, we'll do 5 markers that have been usually asked from the first chapter. So first thing that we will look at is dipoles. So what are dipoles? I've explained so many times, but still if there are people who do not know. So a dipole is when you have two charges, okay? The first charge is positive, the second charge is negative, okay? And they are separated by a distance of 2a, okay? So if you have two charges separated by a distance of 2a, that is a dipole. Yes, Rakshita, SSLC classes are available on this channel. So soon we will be starting. Okay. Soon we will be starting classes for class 10 as well as 11 and 12 simultaneously. Okay. So you can tell all your friends to follow this channel. Whatever content you need, it will all be available on this channel. Okay. Okay. So let me start. Yeah. So question is, derive the expression for electric field at a point on the axis of an electric dipole. So for every dipole, there are two ways in which you can, there are two ways in which the questions will come. One is, if you have a point along the dipole, let's say a point P, along the line of the charge, and if you have a point P perpendicular to the charge. Okay, so if it's parallel or along the line, it's called axial, and if it's perpendicular, that's when it's called equatorial. Okay, so two charges plus q minus q separated by a distance 2a, a point P along the same line. That's when you say electric dipole is axial. Okay, so now let's draw a figure for this. Here we are not considering equatorial, but the next question is for equatorial. Okay, let's do it. Okay, blue. So we will consider a dipole plus q minus q distance 2a. Okay, let's consider a point P on the axis of the dipole. Okay, there's a point P on the axis of a dipole. So point P will experience a field because of plus Q and minus Q. Okay. Now, from the center of the dipole, which is point O, you take a distance R till point P. Okay. So what is R? R is the distance from the center of the dipole to a point P where you have to find out the expression for electric field. Now you have plus Q minus Q, all that is there. So at P, it experiences charges because of plus Q and minus Q. So it has charge minus Q, green. Okay. So positive charge always moves out, right? You've learned that, right? If you have a positive charge, field lines always move out. So since this is a positive charge, the full line will be in outward direction. So EQ plus will be in the outward direction. Negative charge is always inward. So here E minus Q will be in the inward direction. So point P will experience charges in two different directions. Okay. So let's first write down the electric field because of field plus Q. So the general formula for electric field is 1 by 4 pi epsilon naught Q by the distance between the point and the charge. What is the distance? Let's look at that. What is the distance? Okay, I'll take red. So this is the charge P till plus Q. How much is it? This much is A, isn't it? This is A. This is also A. So from plus Q to P, wouldn't it be R minus A? Because this whole thing is R and that small part is A. So this should be R minus A square. Instead of R square, it becomes R minus A square. The direction is P cap. It's along P. Now the electric field due to minus Q will be how much? 1 by 4 pi epsilon naught Q divided by, what is the distance from minus Q all the way till P? So from minus Q till the center of the dipole, it is R. But Q is here. So R plus A. Okay. So from minus P till here is R. Then till here is A. So totally it is R plus A the whole square P cap. Okay. Now the resultant field at point P will be what? Would it be, should you add the electric fields or subtract the electric fields? What do you think? Quickly let me know. Yes. Because the electric fields are in two opposite directions, the resultant will be E plus Q plus E minus Q. So when you add them, you subtract them, because they are in opposite directions. So what you do is, the total resultant electric field will be 1 by 4 pi epsilon naught Q divided by R minus A square minus 1 by 4 pi epsilon 0 Q R minus R plus A square. Or what happened? Yeah. Okay. So this is what happens. The resultant will be the subtraction of the two, because the two electric fields are in two different directions at point P. And then you just solve basic algebra. 1 minus, R minus A square minus 1 by R plus A square. You do the math. So inside the brackets, you will get 4RA R square minus A square. And then you write 4RA into 2RA. Okay. So this 4 you split into 2 into 2. And then 2AQ you write it as P. What is P? P is called dipole moment. Okay. So if you have a dipole, there's a new quantity called dipole moment. Dipole moment means the charge acting on the dipole into the distance between the two dipoles, which is 2A. So dipole moment is given by the alphabet P. That is how you get the final answer. E is equal to 1 by 4 pi epsilon naught 2PR R square minus A square the whole square. Okay. Okay. Now, for a very short dipole, if the distance between the two dipole is very small, then what happens? Then you can just ignore a square and then you can just take r square. Okay, so r square minus a square the whole square becomes r square the whole square, which is r raised to 4. Now the electric field would become E is equal to 1 by 4 pi epsilon naught 2 pr by r raised to 4 p cap, which is 1 by 4 pi epsilon naught 2 p by r cube p cap. Okay? Yes. Okay. I know all basics, my school. Okay. People. Okay. Is this clear? Can you all let me know in the chats? Thank you, Prajwal. I'll definitely take a rest. Okay. Teju says class through this channel. Ma'am, how will it come, ma'am? How will it come, ma'am? Will be the question will be derive an expression for electric field at a point on the axis of an electric dipole. That's how it will come. Okay. So if they ask for axis, then you have to take along the same line on the axis. Okay. Next question. Derive the expression for electric field at a point on the equatorial line of electrical dipole. Okay. So equatorial line, if the question is equatorial line, then you should do the second derivation. So don't get confused, students. There are two derivations for electrical dipole. One is on the axial line, the other is on the equatorial line. Equatorial line means if this is the dipole, the point at which you have to find out the electric field is here. Okay, axial means the point will be here or here along the axis. Okay, let's look at the equatorial derivation for equatorial. Okay, so here the dipole is at minus q plus q. It is at A and B. It is at a point P. We have to find out the electric field at a point P, which is at a distance D from the dipoles. And the two dipoles are separated by 2A. Ma'am, we can derive, ma'am. I didn't understand here. What is the problem? Okay. Now, from A to P, the distance is going to be what? Let me just take this as R, okay? Because in your book, it will be R. So, I will take this as R, okay? Yeah. So, this part is A, this part is A. So, the hypotenuse will be A square plus R square. Here also, it will be A square plus R square. Okay. So again, at point P, because of the positive charge, at point P, because of the positive charge, the field lines will always move out. So if this is a positive charge, field lines always move out. So if this is a positive charge, so field lines should move like this. Now for negative, field lines move to the negative. So if this is a negative, field lines should move like this. Okay. So this is how I get the two directions. Now if my figure was plus Q here, okay, and minus Q here, and point P here, then how will the field lines be? Along plus Q it will be like this, along minus Q it will be like this. This is the direction. Okay, so depending on where you put the plus Q and minus Q, the direction of your EX and EY will change. Now, these two are in really random direction, so you can't do any mathematics with it. So you take the resultant, which is towards the center. So if you make this a triangle, okay, you will get that the vertical components are cos theta. Why it will move? I don't understand your questions. Hi, Afira. The horizontal component is cos theta component. So sin theta components will cancel out. Cos theta component is only what matters. Okay. And then what you do? You write E because of plus Q, E because of minus Q. Same steps. E because of plus Q, E because of minus Q. What will E be? 1 by 4 pi epsilon 0 Q divided by the distance square. How much is the distance? It's going to be A square root of A square plus R square. Square root of A square plus R square. So A square plus R square raised to 3 by 2 because it is the distance square. So square root square. Okay. And then what will you do? Because they are in the same direction, you should add them. See here, because of both the components have cos theta terms and both the cos theta terms are in the same direction. So if the field lines are in the same direction, you have to add them. So here what you do is E plus Q plus E minus Q. In the previous case, you subtracted because the field lines were in opposite direction. Okay. So plus Q, you add them. So what you add? You add equation 1 and equation 2. Okay. You will have a small cos theta element to both. That just shows that, the resultant is along the horizontal axis. So here also there will be cos theta. Here also there will be cos theta. Okay. And then you just add them and solve them. That's all. Simple mathematics. So cos theta can also be written as something else. So if you take this angle as theta, theta is what? Cos theta is what? Adjacent by hypotenuse. So it will be, if you take, this is theta. Yeah, this will also be theta. So it will be R by, I should be better with figures, I know that. So you understand properly. So this is square root of A square plus R square. R by A square plus R square, you take it as cos theta, you substitute that and then you substitute P. P is what? 2AQ, you get the answer. Exam 3 might be easy, might not be easy. I really can't say that yet. But I don't think it will be that easy because it is your third chance. Right? So it's not fair if it becomes easier than the first and the second. So let's see. Let's just hope for the best. Okay? Yes. Okay. Next question. Hi, Nisha. State Gauss law in electrostatics. Derive an expression for electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss law. Okay. So all of these derivations in very utmost detail, I have done a video on Gauss law where I have done all of these three applications, which is one is a straight line, then the sheet, and then spherical sphere. All three are done in that video. You can just go check the video which has been uploaded before this on Gauss law. There is, the thumbnail says Gauss law. Okay. Here also we will discuss it, but not in very much detail. So here what I have is, I have a straight wire. Okay. So I draw a Gaussian surface around the wire. So the Gaussian surface is an imaginary surface that can carry all of the charges. Okay. Okay. So here the best suitable shape for the Gaussian surface is a cylinder. So the length of the cylinder is L, and you find out the electric field at a point P. Okay. So total flux, according to Gauss law, the total flux is always Q by epsilon naught. This is something that we've learned, the total flux. Okay. Now, flux is also equal to EA. EA is what? Electric field into area. What is the area of a cylinder? It is pi r L. So A becomes 2 pi r L. So phi is equal to E into 2 pi r L. Phi is also Q by epsilon naught. And then you find out the total charge. So the total charge enclosed by a Gaussian surface Q is equal to lambda L. How did I get that? I know that this is the surface charge density. This also I've explained in my previous video. So now what will this become? Phi will be lambda L by epsilon naught, and this is going to be equal to E times 2 pi r L. Okay. So from this find out E, very easy. L and L will cancel. E would be lambda divided by 2 f pi epsilon naught. Okay, that's all. This is the first application of Gauss law, infinitely long wire. Okay, so this wire is infinitely long. That's the condition. Okay, clear? Let's move on to the next question. Yes. Hi Ananta, what happened? What happened? Ma'am, JE, you want JE classes? Is that what you're saying? Okay. Students, have you all liked the video? Did you all mark your attendance? Please do like the video. Yes. Okay. Please do like, share and subscribe. Show us your love. Okay. Please do support us so that we can keep giving you wonderful content links. Okay. Derive an expression for electric field at a point due to a charged spherical shell using Gauss law. ಊಟ ಆಯ್ತು. So here what I'm going to do is, I'm going to have a charge. Okay. There is a point charge, and the point charge is inside a small sphere of radius r and a big sphere of radius small r. A big sphere of radius smaller. Okay. So this is the condition. Now what do I have to find out? Electric field at a point due to a charged shell using Gauss law. So there are two cases here. It could be on the outer surface. It could be inside as well. So first thing what we're going to do is, we're going to take flux is what? Flux is E into E dot A, which is EA cos theta, but here area is, electric field is along the direction of the area element. So the angle is going to be 0. So EA becomes just EA cos theta becomes EA. Okay. What is area? 4 pi r square. So phi E into 4 pi r square is Q by epsilon naught. E is equal to Q by 4 pi r square epsilon naught. So this is basic Gauss law. Okay. Now the question is at a point close to the outer surface of the sphere. Okay. So if there is a point P which is outside, that is where R is approximately equal to R, then E is equal to sigma by epsilon naught. Okay. And what is sigma? Sigma is just Q divided by 4 pi epsilon naught, 4 pi R square. Okay. Yes. Let's move on to the next question. So all of this, students, if you want to know all the theory behind it and all that, you can watch the video on Gauss law. Because here if I explain everything, then I won't be able to finish because I have to do 5 markers from every chapter. Okay. Now, obtain an expression for electrostatic potential at a point due to an isolated point charge. So, you have an isolated point charge, okay, plus Q. It is at a distance R from A. And then you bring another charge from infinity, that is Q naught. The distance between Q naught and plus Q is X. Okay. So plus Q, the charge plus Q, let's say it is at O. Okay. The charge plus Q is at O and P is a point at a distance R from O. Let's just put this. P is a point at a distance R from O. Okay, let this point be P. The electric potential at P is the amount of work done in carrying one unit positive charge from infinity to P. Okay, how much ever work it has to do for that charge to come from infinity to this point, that is the electric potential. Now let's consider point A at a distance x from O. So this is point A at a distance x from O. So the electrostatic force at A is what? 1 by 4 pi epsilon 0 Q by what is the distance? Q to A, the distance is x. So 1 by 4 pi epsilon naught Q by x square. Okay. Work done is what? Work done is E dot dx, which is E dx cos 180. Angle is 180, which is minus E dx. Now, so I hope you've all read the question before doing it. The question is, find the expression for electrostatic potential at a point due to an isolated point charge. So what we're going to do is we're going to find out the total work done. So total work done in moving unit plus charge from infinity to the point P is W is equal to dW, which is what? Here we have E minus E dx. So I substitute that here, minus E dx. Now what is E? E I already know, it is 1 by 4 pi epsilon naught Q by x square into dx. Now here 1 by 4 pi epsilon naught is a constant. So I can just take it out. What remains? 1 by x square. Q also I can take it out. Okay. So these are all constants. You don't differentiate, integrate constants. So you can just take it out. Now what remains? Integral of infinity to R. Okay. Infinity to R are the limits. R 1 by x square dx. Okay. So integral of 1 by x square is minus 1 by x. Why? This is just x raised to minus 2 dx, which is minus 2 into x raised to minus 2 plus 1, which is minus 1. So 1 by x square minus 1 by x, not square, minus 1 by x. Okay. Yeah. So, and then you just substitute the limits. Limit is R and infinity. You substitute the limits. You substitute the limits and you will get W is equal to Q divided by 4 pi epsilon naught R. So the work done in electrostatic or electric potential is the same. So whatever value of W you get, the same thing is going to be your V. Okay, it's going to be Q divided by 4 pi epsilon naught R. All right. Okay. Next question. Obtain an expression for the potential energy of an electric dipole placed in a uniform electric field. So consider a capacitor of capacitance C, which is initially uncharged. Okay, when a potential difference V is applied across the capacitor using battery, it acquires a charge Q with one conductor having charge plus Q and another conductor having charge minus Q. Okay, so you have, in this case, what do you have? You have an electric dipole. This is placed inside a electric field. Okay, so the dipole is placed inside a uniform electric field. Now, what we will do is, we will first take the value of formula for potential. Okay, so potential is what? Potential is Q by C. This is the formula from capacitance that we have already learned. Capacitance C is equal to QB. You should know this formula. C is equal to QB is the formula for capacitance. So from that, V is equal to Q by C. Now what we will do, we will find out the work done. Okay, work done is what? Work done is similar to potential. We've already discussed that in the previous question. So it becomes V times dq. So what is V? I substitute Q by C. Okay, so this becomes Q by C into dq. Now this is the work done for a small element. Now what I will do is I will integrate it to find out the work done for the whole element. Okay, so dW is the work done for a small element. Integral of dW, which is W, is the work done for the whole thing. Okay, so let's integrate the whole equation. The integral of dW is 0 to Q, which is equal to integral of 0 to Q by C dQ. Now, C is a constant, capacitance is not going to change. So, I take it outside, what remains is Q dQ. So, you have integral of 0 to Q dQ. Okay. And then, what shall we do? We shall integrate it. So, what is the integral of Q? Q is Q square by 2. Integral of a raised to m is a raised to m plus 1 by m plus 1. So q square by 2. So that is how you get q square by 2. And then you substitute the limits. So you can see here, you get q square by 2 and then you substitute the limits. You substitute q and then you substitute 0 as well. So it becomes capital Q square by 2 minus, instead of Q you put 0. So that becomes minus 0. So W will be Q square divided by 2C. Okay. Hi Hassan. Love from me also. Okay. Now you have to find out the work done. You have found out the work done. You have to find out the potential energy, which is the same. So W and U are same. So every time students, whenever energy is transferred, work is done. So energy transferred and work done, they are always the same. Okay. You can also substitute it in terms of the other formulas. There's another formula for potential energy, which is half CV square. There's also another formula, half QV. These are the three different formulas. Okay, these formulas are just by rearranging Q is equal to CV or C is equal to Q by V and all of that. Okay. Okay. Students, here also in the previous question, it was integration. I think I wrote down here the formula for differentiation. I'm not sure. Okay. Yeah. Okay. Next question. Are you all here with me? Shall we look at the next question? Okay. Define energy density of a charged capacitor. How is the energy density related to electric field present between plates of the capacitor? So the energy density, so this is just a theoretical question. It's just a theoretical question. So what is the energy density of a charged capacitor? It is the energy stored in the electric field between the plates of the capacitor per unit volume. Okay, if you have two plates, the electric field stored between them. That's all. And it's proportional to the electric field between the plates. Equation is half epsilon naught E square. Okay. Next is arrive at the expression for equivalent EMF and internal resistance of two cells connected in series. Okay. So let's do it. So you have two cells. This is the first cell. This is the first cell. This is the second cell. Now you have to show we have to show that the equivalent EMF, which means the EMF of these two and the internal resistance. Okay, just show that that is equal to this. Okay. Now let's consider, okay, obviously how are they connected? These two cells are connected in series. Okay, one after the other. Now let the potentials at points, we'll take 3 points. We'll take 3 points, point A, point B, and point C. Okay. So the potential difference, the potentials at point A, I will take it as VA, B is VB, and C is VC. All 3 points I take. Now, the potential difference between the first cell, the positive and negative of the first cell is how much? The first cell is between point A and point B. So, the potential difference is going to be VA minus VB. Yeah. So that is why first cell is VA minus VB. This is also equal to E minus IR, the general formula for EMF of a cell. Now the potential for the second battery will be between points B and C. So VB minus VC, that is also E minus IR2. Now the total potential will be A to C. Okay, potential across the first battery is A to B. Second battery is B to C. Total potential is A to C. So VAC will be how much? VA minus VC. Now what is VA minus VC? VA minus VB plus VB minus VC. I just add and subtract VB. Okay. Now I substitute the formulas from equation 1 and equation 2 and then I subtract them. I will get VAC is equal to epsilon 1. Sorry, not epsilon 1, E1 plus E2 minus IR1 plus R2. So this E1 plus E2, I will just write it as E equivalent and R1 plus R2, I will write it as R equivalent. So VAC is equal to E equivalent minus I into R equivalent. So E equivalent is E1 plus E2, R equivalent is R1 plus R2. Okay. So this is the formula for equivalent resistance. So you can see this is similar to formula of a single cell. That is why the pictures show that if you have two cells, their equivalent resistance is equal to an internal EMF is equal to having one cell of the same value. Okay? Yes. Is that clear? Shall we move on to the next question? Yes? No? Can I have some fire emojis? Quickly, quickly, can I have some fire emojis? Someone is inviting someone. Please invite me also. Okay, Sri says it's clear. Okay. If Sri says it's clear, let's move on. Karthik has put fire. Is it for the class or for the conversation that's happening? Okay. Now, next next question. Deduce, deduce an expression for. Okay, I'm also invited. Okay, if exam 3 goes well, all of us will go to Karthik's house. It's in Mysore, it seems. Okay. Yeah. Deduce expression for equivalent EMF and equivalent internal resistance when two different cells are connected in parallel. So the previous question was the cells connected in series. Here the cells are connected in parallel. Okay. So you can see the diagram is also different. There is one cell here, another cell here. They are connected in parallel. In the previous case, they were connected in series. Okay. Okay. So, yeah. Now let's find out the equivalent EMF. Same thing, same formulas. In parallel, one thing that you have to know is current is separate. I mean, each component has a different value of current. So, current would always be I1 plus I2. That's the first formula. Okay. So, now in the previous case, here we have taken voltage to be constant. So that is why V is equal to, current to be constant. So V1 is equal to E1 minus IR1. I does not change. So similarly in parallel, V does not change. Okay. There I does not change. Here V does not change. So what does the formula be? V is equal to E1 minus I1R1. Do you see the difference between series and parallel? So in the previous case, V was different. Here V is a constant. There I was a constant. Here I is different. So you rearrange the equations in terms of I. Okay, so for parallel you write it in terms of I1 and I2. In series you write it in terms of V1 and V2. So now let's substitute that here. So we will substitute this and this here. So what is total I1 plus I2? What is I1? This value plus this value. So let's add them. You get this formula. Okay. Now you can write down this much, this whole term as E equivalent and this whole term as R equivalent. Okay. Same thing. It's just similar. You see, when you learn all of these, I want you to relate and learn. Okay, I want you to connect. So, in series, what did you do? You put voltage as varying and you put current same and then you do the steps. Here also you will do the same steps, but you will take voltage constant and current varying. The opposite. Okay? Yes. Let's look at the next question. Deduce the condition for balance of a Wheatstone's bridge using Kirchhoff's law. So for Kirchhoff's law, first thing you need to draw a Wheatstone's bridge. What is Wheatstone's bridge? You have to have 4 resistances. 4 resistances. Okay. And then a galvanometer at the center. So when it's all balanced, when all the resistances are balanced, the galvanometer will not show any deflection. Okay, so that condition is called the balancing condition. So that condition is what we are going to find out now. So when there is zero deflection, the current through the galvanometer is 0. So which means Ig is equal to 0. Okay, now yeah, so you have I1 here, I2, I3, I4. Why do I Why do I need, two same pictures? It's just the same. So I will just erase this. Okay. Okay. Yeah. I1 is the current across branch A, B, B, C, A, D. That's all fine. Let's move on. At node B. Okay. At node B. Control C. Let me just put it here. Control V. Yeah, so you can look at the figure and the data simultaneously. Okay, look at this. At node D, you can say I3 is equal to I1 plus IG. Okay. Yeah. So I3 is what? I1 plus IG. So both of these currents together come and meet at node D. And these two together go here. So I1 and IG comes and they go to I3. Okay. So this is I3. I4 is here. I think when I copy pasted, I4 shifted down. Yeah. I1. Hey, one second. When I copy pasted, it all got different. So I2, I4, I3, I1 is on this arm. This is IG. Okay. Now, I3 is what? I1 plus IG. This we've already learned. I3. Okay. Next, at node B. At node B, I2 is what? Okay. I2 is going to be split into two. Okay. I2 is going to be split into half will go to IG, half will go to I4. Okay. So that is how I get the next equation. I2 is IG plus I4. Okay. Yes. Now, since the bridge is balanced, what happens? In the center, IG is 0. So, well, this also we've learned. In the balancing condition, the galvanometer is not supposed to deflect when all the resistors are equal. So, when all the resistors are equal, that means I1 and I3 have to be equal to I2 and I4. Okay. So, that's the balancing condition. When the lower two resistances are equal to the upper two resistances. So this is the balancing condition. Now let's apply Kirchhoff's law to the loop. Okay. So let's apply Kirchhoff's law to the loop ADBA, which is to this loop we are going to apply Kirchhoff's law. Okay. So let's start. We'll start from I1. Okay. So, yeah, these are the two direction of currents, right? So let's go along I1. So if I take I1 as negative, so whatever sign convention I take at the beginning, I should continue that for the whole loop. Okay. So here, since in the worked out figure, they have taken anything in the direction of movement negative, I will also take it that way. So I'm going to start from here. Now I am going along I1. Okay. I1, R1. So since I'm going along the direction of I1, R1, I'll take it as negative. And then galvanometer Ig, here there is nothing because no deflection, so Ig is 0, so 0. And then here what happens? Here you have I2 R2, but it is in the direction opposite to the direction in which I am coming. I2 R2 is coming like this. I am coming like this. So since it's in opposite direction, I'll take it as positive. Now, if I add these three, you will get the first equation, which is the equation of ADBA. Now, if this is confusing to you and you want to take, if the current or whatever, if anything is measured in the direction in which you move, you want to take it as positive, then what happens? I1 R1 will be positive, I2 R2 will be negative, opposite. So, however sign convention you take, you just have to use the same thing for all the loops. That's the only rule. Now, step 3 is applying Kirchhoff's loop rule to CBDC. So, let's do that as well. So, we're going to apply it to this part. Okay. So, I'll start from I4R4. This is how it is. So let's start from here. Okay. Now this here I will show you when I'm moving in the direction. Okay. So I4R4, if I take it as positive, then I3R3 is in the opposite direction. That I should take it as negative. So if one is positive, the other has to be negative. And then this arm 0. So what happens? You add all that, you will get this equation. So from these two equations, in the first equation you get I2 is I1. Second equation you get I4 is I3. So you just equate it. Okay. So what will you do? You will write I2 times R4 is I1 times R3. How did I get that? Because I2 and I4 are the same. So instead of I4 I write it as I2. Now instead of I3 I write it as I1. Okay, and then you divide it, you will get R1 by R3 is equal to R2 by R4. Okay, so this equation we already know I1 R1 is equal to I2 R2 for balancing condition. But this equation we get it just by modifying this. Okay. Yes, that is the condition for balancing. That is the balancing condition for Wheatstone's bridge. Okay. Let's move on. Yeah, next is a very important, very famous derivation. It's been asked so many times in previous year papers, but I can't tell you if it will be definitely asked in the next exam, but this is a question that has been asked several times. Okay. So here what is it? You have to find out the expression for magnetic field on the axis of a current carrying loop. Okay. So you have a current carrying loop and you want to find out the magnetic field on the axis of the loop. Okay. So what will you do? You take a point P, which is at a distance x from the center. Now P is at a distance r from a point on the loop where you are going to find out the magnetic field. Where you're going to take the element. So there's a small length element dl that you take. dl is at a distance r from a point P. Okay. Now magnetic field will be in which direction? This direction. So this direction cannot be equated. So you take the x part and the y part. Now imagine you take the area element to be this side. Then magnetic field will be like this. And then you will have a dBy and a dBx. So since dBy and dBy are opposite, they just cancel out. Okay. What remains? dBx. So the magnetic field is only going to be because of the x element. That is the first conclusion here. Okay. Magnetic field is going to be only because of x element. Okay. Now you can just use Biot-Savart's law. Once you know the diagram and it's thorough, then it's not that difficult. So Biot-Savart's law is what? dB is equal to mu 0 by 4 pi I dl cross r by r cube. And then r is what? R square plus x square. And you find out the, now what you find? You find out the components. So as I said, y components cancel. So you don't have to consider them. So you only take the x components. So you take dbx. And what is dbx going to be? db cos theta. See, x component is along the x-axis is always going to be b cos theta. So dbx is going to be equal to db cos theta, which is mu 0 by 4 pi I dl by r square cos theta. Cos theta is x by square root of r square plus x square, which is r square equals capital R square plus x square. Then you substitute all of this to the main formula. Okay. Now you get a formula for dbx. But then dbx is not just enough. You need to find bx, which is the magnetic field because of the whole thing. dbx is the magnetic field because of the small element dl. But you need to find out the magnetic field because of the whole thing. So for that, what you do is you take bx is equal to integral of dbx. Now to integrate, everything is a constant. So you kick everything out. What remains is your dl. Only dl remains. Now what is dl? It is the length of the circle. How will you find out the length of the circle? You get the circumference. What is the circumference? Circumference is 2 pi r. Now you substitute, instead of integral dl, you write it as 2 pi r. And then 2 pi, 4 pi, all of those cancel. You will get this final expression. Okay. Now if at the center of the loop, okay, so then point P. So yeah, initially if this was a loop and this was point P, now point P is at the center. So this x is 0 now because there is no point P here. So if x is 0, then your answer will be b is equal to nu 0 ni r square divided by 2r cube, which is equal to nu 0 ni by r. Okay. Yes, diagram is necessary to draw. Okay. For derivations like this, diagram is very important to draw. You can't just by heart the alphabets or the steps and write it. Diagram is very important. Otherwise, some teachers don't give any mark if diagram is not there. Okay. Okay. Yes. Let me just check what's happening here. Is it clear to all of you? Yes, no. Can I have some response? Okay. Students, did you all like the video? Only 12 people liked the video. Others, please quickly like the video. Okay. Thank you, Nishu. Nishu liked. Okay. Okay. Next question. Derive an expression for force per unit length on two infinitely long, thin parallel straight conductors carrying currents and hence define ampere. Okay. So, there are two parallel conductors. Okay. Two parallel straight conductors carrying current. And what happens? They have forces acting F1 and F2. F1, F2. They have current I1 and then I2. The distance between them is going to be D. Now they will experience magnetic fields B1 and B2. Okay. Now you have to derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying currents and hence define ampere. Okay, so the magnetic field B for wire is mu 0 I by 2 pi r, and force for a wire is given by B I L sine theta. Now, depending on whatever wire it is, the values will change. So, F2 will be B1 I2 L sine theta. Now, theta is 90 degrees, so you can just ignore it. So, F2 will be BI2L, which is equal to what is B? Mu 0 I by 2 pi r. So, this B is this B into I2L. So this will become mu 0 I1 I2L by 2 pi r. So if you take F2, this will be the value. If you take F1 also, this will be the value. So both F1 and F2 are equal, which means the force per unit length of the conductor will be this force divided by length, which is the same thing, mu 0 I1 I2 divided by 2 pi r. So that means the force. What are the conclusions that you have here? The conclusions are two long straight parallel conductors carrying current in the same direction attract each other. Two long straight parallel conductors carrying current in opposite directions repel each other. And the force per unit length between the two conductors is F by L, which is mu 0 I1 I2 divided by 2 pi r. Okay. From this you can also define ampere. Yeah. Sorry. It's just checking if the writing part is visible. Hi Sanjay, Sanju. I'm good. How are you? Okay, so from this you can define ampere. So ampere is the force per unit length between two infinitely, to define ampere, you look at the force per unit length between two infinitely long conductors. So you will see that, hi Aradhya, you will see that, see, F by L is equal to nu 0 I1 nu 0 into, imagine the current is 1 and the distance is 1. So 1, 1, 1. So what happens to nu 0 by 2 pi? So it becomes 2 into 10 raised to minus 7. Okay. So that is 1 ampere. 1 ampere is that constant current which maintained in each of the two infinitely long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum causes each conductor to experience a force of 2 into 10 raised to minus 7 Newton per meter length. Okay. That is the definition of 1 ampere. Okay. Nishu, I already mentioned that you liked the video. I am not ignoring you. Hi Aratya. Hi Suchira. Hi Sanjay. Thank you, Aradhya. Okay. So this question is also done. Next question is for moving coil galvanometer. Okay. So I will be back in 5 minutes. Please give me 5 minutes. I want some water. So yeah, we will continue in 5 minutes. Okay. Now, what's the principle behind the working of a moving coil galvanometer? With the help of a neat label diagram, obtain the expression for angular deflection produced in a moving coil galvanometer. Let's look at that. So, what is a galvanometer? Thank you, Nishu. Welcome back to you too. Okay, so a galvanometer is something that is used to detect very small currents. It's not like an ammeter, it cannot detect huge currents, it can detect very small currents. Okay, and what is the principle of a galvanometer? It is based on electromagnetic induction. Okay, so what is a galvanometer based on? Electromagnetic induction. Now, the torque experienced by a current carrying coil in a magnetic field is mainly because of this electromagnetic induction. Now, this is the structure of a moving coil galvanometer. So, those of you who can learn it, it is good if you can learn it. So, you can see there's a coil. Okay, there's a coil, and to this coil, a needle is connected. Okay, so when the coil rotates, what happens? The needle will keep moving. So the needle moves on a scale. So wherever the needle moves, you get to read the value because it is stuck onto a scale. And then there is a north pole and a south pole. Between the north pole and the south pole, the north pole and the south pole, they are both permanent magnets. Okay, so yeah, that the steps I just explained here. There's a rectangular coil. There's a magnetic field provided by strong magnets. And there's a core. There's a spring. And there's a pointer. Okay. Am I not audible? Yes, Aradhya. What happened? Okay. When current flows through the coil, okay, that is inside the magnetic field, what happens? It experiences a torque, and the torque is given by torque is equal to NIAB. Okay, where what is N? Number of turns, I is the current, A is the area, B is the magnetic field strength. So the magnetic torque, what does the magnetic torque do? It rotates the coil. Okay, yes. Now, yeah, so torque, not torque. Yeah, the torque of the spring is K phi. So if you equate these two, you will get K phi is equal to NIAB. And from this, you can get the equation phi is equal to NAB by K into I. So from this, it's very clear that phi is directly proportional to I, which means the angular deflection is directly proportional to current. Okay. So if angular deflection has to be proportional to current, then NAB by K should be a constant as well. Okay? Yes. Okay, next we will do some questions on refraction and lenses and all that. So first thing, refraction at a spherical surface. Okay? So the question could be show that the refraction at a spherical surface is given by some formula or anything like that. Or, this won't be as a question, but using this formula, we will do questions. So this is a formula. Before deriving the lens maker's formula, there was a formula which is the spherical surface refraction formula. Okay, so this formula gives you the relationship between refractive index of the object, refractive index of the image, object distance, image distance, and radius of curvature. Okay, so N2 is the refractive index of the object divided by V is the image minus N1 is the refractive index of medium U is the object. This is N2 minus N1 by. Okay. I am from here only. Okay. Yeah. Next is question. What is the question? Derive lens maker's formula. How do you derive lens maker's formula? First thing is you need to know the figure. So even for this question, figure is very important. Figure is very important in questions like these. Okay. So how will you do that? You take a lens. Okay. You take a lens. You take an axis. So initially, a ray of light passes through the lens. It bends. You get an image here. Okay. So in this case, what we are going to do is we are going to ignore the second surface. So you imagine that there is only one surface for the lens. So this surface, you ignore it. So what happens? It bends, you get the image. You're just assuming there is only one surface. Okay. But in reality, there are two surfaces. So now what you do for the second surface, you take the image of the first surface as the object of the second surface. Did that sound like gibberish? You take the image. Okay, this is the image of the first surface. This you will take object as this. So now this is going to form another image here. So I dash is the image of I. Okay, so the first object is O, second object is I. So you can look at this figure here. So this is how it's initially taken. You know there's only one object and the object produces an image here. Now this image produces another image here. That is why I have I and I1. Okay, so I is the image because of the object. I1 is the image because of I. Yeah? You don't understand the diagram? Which diagram, Nishu? This diagram? Why? Why? What happened? See, the diagram is not complicated. You have a lens, okay? You have a principal axis. You have an object. So what happens? Light ray passes through the lens. It is reflected. You get the image here. Okay? Is this much clear? Now, right now, what I'm considering is the first surface of the lens. So I'm just ignoring the second surface of the lens. Then this distance is object distance. This is image distance. Everything is okay. Now, if there is the second surface of the lens, okay, there should be two refractions. See, from here, you can see, here you can actually see clearly. So here, this is refracted only by this surface and it's forming the image here. But if there is one more surface, won't it bend again? So if the second surface is also there, then the image is going to be produced here, like at another point. Okay? If it was just because of invigilator issues that you lost marks, then you can just pray, dear. Next time you'll get a good invigilator. Okay? Yeah. Don't worry. So now you have two images. So the first object and the first image is from the first surface of the lens. And for the second surface of the lens, the first image will form object and then you will have one more image. Okay. And then let's look at the derivation part. So image distance, object distance, radius of curvature, and then you substitute all of this in the equation that I just showed you. Okay. This is the refraction at the first surface. Now for the second surface, what you do? You will take the first, here you see, image was BI1. So here you take object as BI1. That's the only trick part here. Okay. So the object of the image of the first surface serves as object of second surface. Okay, then you substitute it in the formula and then add the two equations, you will get this final answer. Okay, now in case if the object is at infinity, so if u is at infinity, then what happens? 1 by u will be equal to what? 0. 1 by infinity, which is 0. Okay, and v will be equal to f. So you will get this formula. And that's how you get the very famous lens maker's formula. 1 by f is equal to n2 minus n1 minus 1, 1 by r1 minus 1 by r2. Okay. So this formula is known as lens maker's formula, and this formula can be used to find out the focal length of a lens. Okay. Next question. Derive the expression for combination of two thin lenses in contact. So here also you can see, if only the first lens L1 was there, the image would have been formed at I1. Now if L2 is also there, the image is formed at I1. Okay. So see, this and the previous question is similar. There you have two surfaces. Here you have two lenses. That's the difference. Okay. Now, if you have refraction through lens A, what is the lens maker's formula? 1 by V minus 1 by U is 1 by F. So V is V1. And then F is F1. So 1 by V1 minus 1 by U by 1 by F1. Now for through lens B, what is 1 by V? You see the object becomes the image. So U will become V1. 1V minus 1 by V1 is 1 by F2, and then you just add the 2. You will get 1 by V minus 1 by U equals 1 by F. So if you look at these equations, this is 1 by F, this is also 1 by F. So you can write 1 by F is equal to 1 by F1 plus 1 by F2. So if you simply add it, you will get it. Okay. So if you have three lenses, then what happens? You can just add the focal lengths. Okay. You want one short video of 5 most important chapters. Okay, let's see. I'll try. I'm not going to promise you, but I will try. Okay, I'll try my best. Okay. Now, next question. Derive the expression for refractive index of the material of the prism in terms of angle of minimum deviation and angle of prism. So here also diagram is very important. You have a ray. Okay. Now if the prism was absent, the ray would have moved like this. But the prism is there. Okay. The prism is there. So what happens? The ray bends. The ray bends like this. So the ray bends. Now if the second surface was absent, then the ray would have passed straight, but it's there. So what happens? The ray bends again. Okay. Now what are the normals? The normals are these two lines. So, angle, the deviation from the initial path. So, initial incident ray is bent. So, the deviation is this much. This is delta 1. Now, the second deviation is this much. Now, when you extend this backwards, you will get this delta. Okay, so that delta is the total deviation. The first ray deviation, the second ray deviation, together you get delta. Okay, now A, this is the angle of prism. Now with this much things, you can do this derivation. Okay, from tomorrow, 5 days, 5 chapters. Okay, so if you want 5 days, 5 chapters, you have to, I want people. Only if I have people in my class, then I can do the class. Otherwise, I will not be able to conduct the session. So to conduct the session, we need to have students in class. Okay. So if you go bring all your friends and under this video, you comment. Okay. And tell, I want to know how many people are interested. If there are a lot of people, then we will definitely have the class. Okay. Yeah. So bring all your friends. Ask all your friends to come in. Come and let me know in the comments. So now, what is the equation for prism? R1 plus R2 is A. And then what is deviation? This is just from the triangles. See, if you look at this one, this is I1 and this is the same as delta 1 minus delta 1 R1. Okay, so instead of delta 1, instead of I1, you can write it as delta 1 plus R1, or you can write it as I1 minus R1. So that's how you get this equation. Okay. Bye, Kunal. Done? Are you going to sleep? Malu, VR PDF I'll upload. Okay. Yeah, I'll upload after the class. Now this is a graph. This is a graph for angle of deviation and angle of incidence. So this is this thing. Okay. So this is I1 equals I2. This is the lowest point. This is the angle of minimum deviation. Okay. Maluviar, I haven't uploaded it. Okay. I'm sorry, I will upload it. Today, yeah, today or tomorrow you check, it will be there. Okay. Yeah. So for minimum deviation, what will you do? Where did I stop? Yeah. Okay. R1 plus R2 is A. From this triangle, R1 plus R2. See, this is A. This is also A. So R1 plus R2 should be equal to A. Now, since, if all these are proper, then R1 and R2 should be equal to R. So which means 2R should be equal to A. So R is A by 2, which means if you substitute this in equation 3, you will get 2I minus A. So I is A plus dm by 2. Now, this you can substitute easily in Snell's law. So what is Snell's law? N is equal to sin I by sin R. Now, what is I? A plus D by 2 and R is A by 2. So, if you just substitute the values of I as A plus dm by 2 and R as A by 2, you will get this final answer. Okay. Bharati, I did so many MCQs for exam 2. Yes. So, see, those are MCQs from your PU chapters. So, the same MCQs can come from exam 3 as well. For exam 3, portions are not going to change. Okay, only questions will change. So, MCQs from that can come, cannot come. It may come or may not come. But those are definitely MCQs that you can practice for exam 3 as well. Okay. Exam 1, exam 2, exam 3, all of it has same portions, right? The only thing is the question paper is different. Okay. So the content that we can give you is the same. Okay. Oh, very good. Bharati got 15 out of 15 for MCQs. Very good. Was that because of, did my 100 MCQ video help you, dear? Yeah. Next question. Okay, I'm very happy. Yeah, you can use the same thing for exam 3 as well. So if you have, if things like this happen, please let me know in the comments, okay? Because this makes me really happy. Okay? So please comment under the video. Let me know, you did watch the video and you got 15 out of 15 and all. Let me know all that. Okay? Yeah. And I'm very happy to hear from you. Next question. Two coherent waves of a constant phase difference undergo interference. Obtain the expression for the resultant displacement. Okay, how do you do that? First thing you define, okay, what is happening here? You have two coherent waves, one wave, they meet together at one point, okay, they interfere. So let the first wave be y1, let the second wave be y2, okay. So y1 I define as a1 sine omega t, y2 I define as a2 sine omega t plus phi. Now, when you add these two, when you add y1 and y2, what will you get? A1 sine omega t plus a2 sine omega t plus phi. A1 sine omega t plus a2 sine omega t plus phi. Now, what I will do? Math, basic math. This you might have learned in your math class. Sine theta plus phi is what? Means sine a plus b. Sine a plus b is what? Sin A sin B plus, sorry, what am I saying? Sin A cos B plus cos A sin B. Okay? Sin A cos B plus cos A sin B. Now what I will do is I will take all the common terms outside. Okay? So I have A1 sin omega t and then a2 sin omega t cos phi. So in both of these, sin omega t is common. So I can take sin omega t outside. What remains? a1 plus a2 cos phi. Okay. a1 plus a2 cos phi into sin omega t plus a2 sin phi cos omega t. Now r cos theta will be what? The resultant. It will be this much. This is going to be r cos theta. A1 plus A2 cos phi. Okay. So r sin theta is going to be A2 sin phi. And y is going to be equal to what? The resultant. Cos theta sin omega t plus sin theta cos omega t. So y is equal to r sin omega t plus theta. Okay. Oh, Haswin also got 15 on 50 for MCQs. Okay, very good. So all of these students, they have watched a video which says 100 MCQs for physics. Okay, that is there in Vedantu Karnataka YouTube channel. Students, thank you so much. All these comments mean a lot. Can you all go under the video and mention this in the comments as well? Yeah, because I forget your names. Once the live is done, then I can't see the live chat. So can you go comment under the video? It will mean a lot to me. Hi, Amsu. Okay. Expression for amplitude of resultant wave. So, to find out the expression for amplitude, the final expression is Final expression is R is equal to a1 square plus a2 square plus 2a1 a2 cos phi. Now how did I get that? I just squared everything here. Okay. So r square cos square. You just square and add equations 1 and 2. Okay. You square and add equations 1 and 2. You will get this answer. This is all just maths. You can do it. I know all of you. You're all smart students. You can all do it. Okay. So what is it? What is there here? R square cos square theta plus R square sin square theta is equal to A1 plus A2 cos phi the whole square plus A2 sin square phi. Okay. So cos square theta plus sin square theta, you take it outside, this becomes 1. So this will be A1 square plus A2 square cos square phi plus 2A1 A2 cos phi plus A square sin square phi. Now this is going to be equal to cos square theta plus sin square theta is 1. So it goes away. What remains? R square plus A1 square plus A2 square plus 2 A1 A2 cos theta or phi, whatever angle you want to put. Okay. Okay. Next is path difference between resultant wave and first wave. Path difference is always tan theta, and tan theta is A2 sin phi divided by A1 plus A2 cos phi. And the relationship between intensity and amplitude is given by I is proportional to A square. Okay? Okay. Next. Write the conditions for constructive and destructive interference in terms of phase difference. Okay. So you have to find out the condition for constructive interference and the condition for destructive interference, and that has to be written in terms of phase difference. Okay. Nishu wants to know what's for my dinner. I'm eating, I don't know, I have to make my dinner. Okay. Yeah. After a certain age, your mom won't make you dinner. You have to make it by yourself. Now life is good when you're students. So all of you can enjoy your life to the fullest. The only worry you have is exam, no? Exam is all chill. Next, first we will look at the condition for constructive interference. So what happens? So now I'll tell you what is constructive interference and what is destructive interference. So imagine you have a wave like this. Okay. You have another wave like this. They superimpose, and what happens? You get a big wave. Okay. You will get a big wave. That is constructive interference. Okay. Now, destructive interference is when you have one wave and the second wave is oppositely phased, such that when they join together, you get nothing. You get a blank line. You get a dark region. That is destructive interference. Okay. Constructive interference is when you have these two waves that join together. Destructive is when the two waves are there and they disappear. You just get a dark space. Okay. Okay. Yeah. So resultant, we've already looked at the formula A1 square plus A2 square plus 2A1 A2 cos phi. Now, the amplitude will be maximum when cos phi is plus 1. Okay. And phi is equal to 0, 2 pi, 3 pi, 4 pi. Phi is what? 0, 2 pi, 3 pi, 4 pi, 4 pi, 5 pi, how many ever. So you can just write it as 2n pi. Okay, generally it's going to be 2n pi, where n can take numbers 0, 1, 2, 3, 4, etc. Okay, so now R max will be A1 square plus A2 square plus 2A1 A2, which is A1 plus A2. Next, conditions for destructive interference. Conditions for destructive interference is when phi is equal to 2n plus 1 pi. Okay. So here there is a small correction. This would be 3 won't be there. 2, 4, 6, 8, it will be like that. Okay. Yes. This is the value for maximum, minimum amplitude. Okay. Bharati Kumar is our, influencer. She's promoting our channel. So Bharati got 15 out of 15 only depending on Vedantu Karnataka. See, people trust us. Thank you, Bharati. Next, what is photoelectric effect? Write experimental observations of photoelectric effect. So photoelectric effect is, history and all is not required. So what is photoelectric effect? It is the emission of electrons that occur immediately when something strikes a metal. Like, let's say there's a metal surface. Okay, there's a metal surface. There's a metal surface and, an electron comes, some high energy particle comes. As soon as it strikes the metal, what happens? An electron is ejected. Okay, so the time delay between the incidence of radiation, where the radiation comes and hits, and the emission of electron is typically 10 raised to minus 9 seconds. 10 raised to minus 9 seconds. Can you imagine that? How small is that? See, 10 seconds itself is quick. 1 second is fast. So imagine 0.000 that much seconds. So the moment a high energy radiation hits a metal, an electron is ejected. The time lag is very small. That is why you can say it is an instantaneous process. Why can you say it's an instantaneous process? Because it's quick. It's very fast. See, I can't even spell a word or a letter in less than 1 second. So how small a fraction of a second is, or how small could 10 raised to minus 9 seconds be? Okay, next is threshold frequency. So for every metal there is a minimum frequency, okay, of the incident radiation. Only if the incident radiation has a frequency above that, it will emit electron. That is one condition. Okay, so if I just send any any radiation, it won't eject electrons. The radiation should have a frequency which is greater than the minimum frequency that is required to eject an electron. So that's threshold frequency. And then effective radiation intensity and photocurrent. So for any given photometal and the frequency coming in, it is greater than the threshold, then the electron produced, okay, the electron is emitted. So this electron is responsible for photoelectric current, and the emitted electron responsible for photoelectric current is directly proportional to, intensity of incident radiation. The intensity of incident radiation. And the photocurrent is independent of the frequency. Okay? Yeah, it is independent of frequency of incident radiation. Okay? Next is the effect of radiation frequency on kinetic energy of emitted electrons. Now, for a given metal, imagine there's a frequency of radiation coming in. Frequency is above threshold. The maximum kinetic energy of the electrons that are emitted will always be directly proportional to the frequency of the incident radiation. Maximum kinetic energy directly proportional to frequency of incident radiation. So the kinetic energy of the emitted electron is independent of the intensity of incident radiation. So all of these points are very important. So these are the observations that led to the development of a theory called as the quantum theory of light. Okay, so it is in the quantum theory of light that the theory came that light behaves as packets. Light has packets of energies called photons, and each photon is related to its frequency, by which relation E is equal to hf or h nu. Okay, so E is equal to h nu was derived from these relationships. These were all analyzed by famous scientists. They did lots and lots of work and they found out all of this. Okay, now let's write Einstein's photoelectric equation. Also using this, explain the experimental observations of photoelectric effect. Okay, let's do that. Let's find out Einstein's photoelectric effect. Yeah. Einstein explained the photoelectric effect based on Planck's quantum theory. According to Planck's theory, light consists of tiny packets of energy called photons, something we already learned. Yeah. He proposed that photoelectric effect results from an elastic collision between a photon of incident radiation and a free electron inside the photometal. So the energy of each photon is E is equal to h nu. Okay, what is h? H is Planck's constant, nu is the frequency of light. Now, when a photon with energy h nu strikes the metal, the energy is used in two ways. Okay, so there's a frequency h nu coming, it is going to hit a metal. So when it hits the metal, the energy is going to be used in two ways. What are the ways? First one, it will eject an electron. Second, the remaining energy, the amount of energy that falls, half of it, not half of it, how much ever the electron wants to get out of the metal, it takes it. The rest of the energy is used to impart kinetic energy to the emitted electron. Okay? Yes. And thus, Einstein's equation for photoelectric effect is h nu is equal to h nu is equal to phi plus kinetic energy maximum. So h nu is equal to what? What is phi? Phi is the minimum energy required for the electron to be ejected plus the maximum kinetic energy. So from this, kinetic energy is what? H nu minus phi. Okay. Now, if the work function phi naught is h nu naught, okay, if this is h nu naught, then the equation can be modified and written like this. Okay. Okay. Next is the explanation of experimental observation using Einstein's equation. Same thing, we already discussed this. Okay, this is just repetition. Next, what is a rectifier? Explain the working of a PN junction diode as a full wave rectifier with circuit and input-output waveforms. Okay, so a full wave rectifier is a rectifier in which current flows only through, current flows during the entire cycle. Okay, so for a full wave rectifier, let's see. So all of us know that diode is a device that conducts current only in one direction, right? So if you have a diode and the diode conducts in this direction, then it will not conduct in the opposite direction. It's like a battery on your TV remote. Okay, I don't know, on your TV remote there's batteries, right? So if you have to put the battery in one direction. If you put it in the other way, the remote won't work. Similarly, diode is also they're two different things, but diode also works on the same thing. So diode also works only when it is connected to the battery in one particular direction. So it has to be connected properly. Otherwise, it does not allow current to pass through. But then, you know, this one little thing can be used in a full wave and a half wave rectifier. Do I have half wave? Yes, I have half wave as well. Okay. So what I'm going to use is I'm going to use this principle for a full wave and a half wave rectifier. Okay. So now this is an input AC, and then there is a transformer. Okay. And then there is a diode, another diode. Okay. And then, yeah. So you can see during the first half cycle, okay, during the first half cycle, what happens? Current passes through diode D1, but current does not pass through diode D2. So there is one, you know, uphill for diode D1, diode D2 is 0. Now in the second half cycle, you can see diode D2 conduct, but diode D1 does not conduct. That is why now there is a negative part in diode D2, because D2 is conducting, D1 is not conducting. Again, D1 conducts, D2, D1, D2. So it alternately conducts. So what is the result? You have a full AC wave. What is an AC wave? AC current is current that appears in two half cycles. There's a positive and the negative. Current flows in both the directions. So that is what happens for a diode. I mean, for a full wave AC to DC. I was not feeling well, but now I'm okay, dear. Don't worry. See, I don't understand. Yeah. And then what happens? It gets converted into DC. Yes. PVG was already giving me the answer. Very good, PVG. Which session have I? Yeah. Okay. Now, output DC you will get. So, one small correction is here. This is the input, okay? So, input is AC, and what I had to draw was here, but I drew it here. So, diode D1 first conducts, D2 is 0, and then D2 conducts, D1 is 0, and then D1 conducts again, D2, D1, D2. So, it just keeps on conducting like that. Okay, so that is why, say, if you see the difference between half wave and full wave, see, for a half wave, you can see there's one, uphill, and then there's a space, and then there's another uphill. That is because, yes, Soumya, it is DC. Very good. It is because, there is only one diode. Okay, so one diode can conduct in one half cycle. The next half cycle, it does not conduct. So there's no output, zero output. Again, the next half cycle, it conducts. So instead of that, if you have two diodes, in every half cycle, they continuously conduct. Okay, so you can see this. During the positive half cycle, what happens? One second. Yeah. During the past positive half cycles, what happens? When the end of the A is positive, when A is positive with respect to C, B becomes negative. A is positive, B is negative, D1 is forward, bias. Yes, Neha, if you follow all the videos, everything in our Vedantu Karnataka channel, you will definitely pass. Okay, but be thorough. Don't just watch the video and go. You have to practice all the derivations because otherwise you will get stuck during your exam. Okay, see, one main problem with derivations is if you don't keep practicing, you should at least write 3 times. Otherwise, for your exam, when you go sit there and start writing, you will get stuck in between. You will forget and then you will lose marks. Okay, so that shouldn't happen. So be thorough with whatever is done here. Don't just watch the videos and go for your exam. Study what is given in the videos and then go for your exam. Okay, I won't say you will get out because for out, you definitely need to know your concepts very well. Okay, these are all important questions. Okay, for out, you need to take a little more effort. Hmm. Oh, forward biased. So initially, A is positive, B is negative, and then diode D1 is forward biased. Then, so this is the input signal, right? This is when the input signal is this. Now, when this part comes, when the negative half cycle of AC comes to the diode, then what happens? Then what happens? Then A will be negative, B will be positive. So if A is negative, then this will become reverse biased. Yes. So D1 will become reverse biased and then it will not conduct. Now B is now positive. So what happens? B will become forward biased. So B1 will become forward biased. So what will the output be for this? Yeah. For this, the output will be this. For this, the output will be this. This is because of diodes D1 and D2. Okay. So this is for a rectifier, a full wave rectifier. Now there is half wave rectifier also. For half wave rectifier, what is the difference? There is only a single diode. So when A is positive, it can conduct, but when A is negative, it will be in reverse biased. So it will not conduct because only one diode is there. In full wave, what was happening? When A is positive, A will conduct. When A is negative, the other diode is conducting. There's something always conducting. That is why you have a continuous DC wave. But in half wave, you have only one diode. So only if A is positive, it will conduct. But then you give an input AC, so A cannot always be positive. Here A will be positive. Here A will be positive. Here A will be negative. Here A will be positive. So whenever A is negative, there is no conduction. That is why you have this following output. So when A is positive, okay, I will draw it here. So when A is positive, output is there. When A is negative, the diode does not conduct. Again, when A is positive, diode conducts. A is negative, diode does not conduct. A is positive, diode conducts. It just keeps on moving like that. Okay. Now, when does this happen? I will draw the simultaneous AC waveform here. So, see, when the AC signal is negative, that is when A becomes negative. That is when A does not conduct. So when sine wave or the AC signal is positive, A is positive, it will conduct. So the colorful line that you see is your input signal. The pink line is your output signal. Okay. So for half wave, when A becomes positive, the diode becomes forward biased and then it conducts. When A is negative relative to B, the diode becomes reverse biased. Okay. So the diode does not conduct and no current flows through the load resistance. Okay. So in a half wave rectifier, current flows through the circuit only during the positive half cycle of the input and no current flows through the negative half cycle. This results in an output signal that is a series of pulses corresponding to positive half of the AC signal. Okay? Okay? So these are all some. Okay. Yeah. So these are all some important 5 mark questions. Okay. I've not discussed all the 5 markers here, but some 5 markers that are very commonly asked in exams that I have discussed here. Okay. There are still 5 markers that you have to look into your textbooks if you want centum and all that. These are all some important 5 markers. Okay. So, students, let me know what all sessions you want for your exam 3. Please let me know under this video itself. If you can let me know today itself, we can plan accordingly what all sessions you want for your exam 3, because we have to give you content that you want, right? Because we are doing all this for all of you. Okay? So, all the best for your exam 3. I mean, we will have more videos, we'll definitely have more classes. So, anything else? If you have any doubts, you can ask me now. Otherwise, we will wind up. I'm not very sure, Supreet. I have to find out. I'm not sure. Okay? Yeah. Welcome, Sri. Yes. Okay? So I will see you with another video in another class. Okay? So please tell all your friends. Okay? Please tell all your friends that Vedantu Karnataka has classes that you can attend for your exam 3, KCET, COMEDK, whatever you want. We're here for all of that. Okay? So whatever classes you want, just let us know in the comments. And if you've enjoyed the class, let me know that also, because I'll be very happy to hear from all of you. Okay? Please do like the session and subscribe and share it to all your friends. Okay? So I'll see you with another video. Bye Saumya. Bye Supreeta. Meet Supreet. Bye Sri. Bye bye. Bye all of you.